Welcome to our journey through the cosmos, where we'll explore the strangest stars in the universe. From pulsars to magnetars, these celestial bodies defy the laws of physics and boggle the mind. They are the cosmic lighthouses and the stellar remnants, the ultra-dense objects and the bizarre formations that make the universe a truly fascinating place. Prepare to be captivated by stories of stellar evolution, the death throes of massive stars, and the incredible forces at play in the cosmos. We'll delve into the hearts of supernovae, where these strange stars are born, and examine the mind-bending physics that govern their existence. Fasten your seatbelts, space explorers, as we embark on an awe-inspiring adventure to the edges of our understanding, where the familiar laws of nature are bent, broken, and rewritten. Let's set our course for the most bizarre and fascinating corners of our universe. Imagine a star, not just any star, but one that's denser than an atom, spinning hundreds of times per second and beaming out radio waves like a celestial lighthouse. That's a pulsar, my friends, a bizarre and fascinating object born from the death throes of a massive star. You see, when a star significantly larger than our sun runs out of fuel, it collapses under its own gravity, its core imploding in a spectacular supernova explosion. What remains in some cases is a neutron star, a sphere so dense that a teaspoonful of it would weigh billions of tons here on Earth. Now these neutron stars are already pretty strange, but pulsars take it to another level. They spin incredibly fast, some making hundreds of rotations every second thanks to the conservation of angular momentum. Think of a figure skater pulling in their arms to spin faster. It's the same principle. But here's where it gets really interesting. Pulsars have incredibly strong magnetic fields, trillions of times stronger than Earth's. These magnetic fields funnel charged particles, forcing them to stream out from the poles in intense beams of radiation. These beams, like cosmic lighthouses, sweep across the universe as the pulsar spins. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation, hence the name pulsar. The discovery of pulsars in the 1960s sent shockwaves through the scientific community. Here were these incredibly precise rapid pulses of radio waves coming from deep space. Some scientists even speculated they might be signals from extraterrestrial civilizations. While the alien hypothesis was eventually ruled out, pulsars remain one of the most fascinating and useful tools in astrophysics. By studying their pulses, we can learn about the extreme physics at play in neutron stars, probe the interstellar medium, and even test Einstein's theory of general relativity. So, the next time you look up at the night sky, remember the pulsars, those cosmic lighthouses spinning madly in the darkness, remnants of stars long gone but still illuminating the universe with their strange and powerful beams. If pulsars are the lighthouses of the universe, then magnetars are the explosive beacons, capable of unleashing unimaginable amounts of energy in the blink of an eye. These are the cosmic powerhouses, the magnetic monsters that put even the most extreme objects to shame. Imagine a magnetic field so strong that it could distort the atoms in your body from thousands of miles away. That, my friends, is the power of a magnetar, a special type of neutron star with a magnetic field 1,000 times stronger than even a typical pulsar. These magnetic fields are so intense that they can cause the very fabric of spacetime to warp and crack. They can trigger starquakes, massive tremors on the surface of the magnetar, that release bursts of gamma rays and X-rays with incredible luminosity. To give you a sense of scale, a single magnetar outburst can release more energy in a fraction of a second than our sun will emit in its entire 10 billion year lifespan. That's the kind of power we're talking about here. But what creates these magnetic monsters? The exact mechanism is still a mystery, but scientists believe it has to do with the formation of the neutron star itself. During the supernova explosion, if the collapsing core is spinning incredibly fast and has a strong magnetic field to begin with, it can amplify that field to unimaginable levels, giving birth to a magnetar. Now you might think that with their extreme nature, magnetars would be incredibly rare, and you wouldn't be wrong. We've only detected a handful of these objects in our galaxy so far, and each discovery is a cause for excitement in the astronomical community. Studying magnetars allows us to peer into the most extreme environments in the universe and test the limits of our understanding of physics. They are natural laboratories for studying the behavior of matter under extreme pressures and magnetic fields, conditions that we could never replicate here on Earth. So, while they might be rare and elusive, magnetars are a powerful reminder of the incredible forces at play in the cosmos. They are a testament to the fact that the universe is full of surprises, and that we still have much to learn about the strange and wonderful objects that inhabit it. We've journeyed through the cosmos, exploring the bizarre realms of pulsars and magnetars. But our adventure into the heart of stellar strangeness doesn't end there. Let's venture now into the hypothetical realm of quark stars, objects so dense they challenge the very limits of physics as we know it. Imagine a star, not just composed of atoms or even densely packed neutrons, but of quarks, the fundamental building blocks of matter. These hypothetical objects, known as quark stars, are thought to exist in a realm of density exceeding even that of neutron stars. You see, in a neutron star, the immense gravitational pressure is so great that electrons are forced into protons, creating a sea of neutrons. But what happens when the pressure is even greater? Some theories suggest that neutrons themselves might break down, releasing their constituent quarks. These quarks, no longer confined within individual neutrons, would form a sort of quark soup, a state of matter that physicists call strange matter. This strange matter is thought to be incredibly dense and stable, potentially even more so than the material found within neutron stars. Now, the existence of quark stars is still very much in the realm of theoretical physics. We haven't conclusively observed one yet, but there have been tantalizing hints and observations that suggest their presence in the vast cosmic ocean. One of the telltale signs of a quark star would be its size. Because of the extreme density of strange matter, a quark star would be significantly smaller than a neutron star of the same mass. So if we were to observe an object that seems too small for its weight, it could be a strong candidate for a quark star. Another clue might lie in the radiation emitted by these objects. Quark stars are predicted to cool down much faster than neutron stars, leading to differences in their X-ray emissions. The search for quark stars is a testament to the human thirst for knowledge and our fascination with the unknown. It pushes the boundaries of our understanding and drives us to develop new technologies and techniques to explore the universe around us. While their existence remains unconfirmed, the possibility of quark stars is a captivating reminder that the universe is full of mysteries, waiting to be unraveled. It's a call to keep exploring, keep questioning, and keep pushing the boundaries of our knowledge. For who knows what other wonders await us in the vast cosmic tapestry. In the cosmic graveyard where massive stars meet their dramatic demise, lie the remnants of their former glory neutron stars. These incredibly dense objects, born from the fiery heart of a supernova, are a testament to the extreme physics that govern our universe. Imagine a sphere no larger than a city, yet containing more mass than our entire sun. That, my friends, is the reality of a neutron star, a cosmic object so dense that a single teaspoonful of its material would weigh billions of tons here on Earth. These stellar ghosts are the remnants of massive stars, those at least 8 times more massive than our sun, that have reached the end of their life cycle. When such a star exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses in on itself, triggering a shockwave that rips the star apart in a spectacular supernova explosion. What remains, in the aftermath of this cosmic cataclysm, is the incredibly dense core, compressed by gravity to unimaginable levels. The protons and electrons in the atoms are squeezed together, forming a sea of neutrons, hence the name neutron star. The conditions within a neutron star are mind-boggling. The gravity is so intense that time itself is warped, slowing down significantly compared to time as we experience it on Earth. The surface of a neutron star is incredibly hot, millions of degrees Celsius, and emits intense radiation across the electromagnetic spectrum. Neutron stars are not just fascinating objects of study, they are also incredibly useful tools for astronomers. Their precise radio pulses, like those from pulsars, act as cosmic clocks, allowing us to study the interstellar medium and test Einstein's theory of general relativity. Furthermore, the extreme gravity of neutron stars makes them ideal laboratories for studying the behavior of matter under extreme conditions. By observing how light bends around neutron stars, we can learn about the properties of gravity and the nature of spacetime itself. So the next time you gaze up at the night sky, remember the neutron stars, those tiny, incredibly dense remnants of stellar explosions. They are a testament to the power of gravity, the cycle of stellar life and death, and the endless capacity of the universe to surprise and amaze us. Our exploration of the universe's strangest stars takes us now from the extreme density of neutron stars to the quieter yet equally fascinating realm of white dwarfs. These stellar remnants, often overlooked in the cosmic drama, offer a glimpse into the future of our own sun. Imagine a star, not collapsing under its own weight, but gently cooling down, its surface glowing with the residual heat of a long life. That, my friends, is the essence of a white dwarf, the final evolutionary stage for most stars in the universe, including our own sun. Unlike their massive counterparts that end their lives in supernovae, stars like our sun are destined for a less dramatic but equally fascinating fate. As these stars exhaust their nuclear fuel, they shed their outer layers into space, creating beautiful planetary nebulae. What remains is the core, a dense ball of primarily carbon and oxygen, no larger than the Earth but containing a mass comparable to our sun. This stellar ember, no longer generating energy through nuclear fusion, is a white dwarf. White dwarfs shine with the residual heat from their former lives, slowly radiating their energy into space over billions of years. As they cool, their color changes, shifting from white to yellow, orange, and eventually red. These stellar remnants, though small, are incredibly dense. A teaspoonful of white dwarf material would weigh several tons here on Earth. This density is due to the tight packing of electrons within the star, a consequence of quantum mechanics. White dwarfs, while not as flashy as their supernova-producing counterparts, play a crucial role in our understanding of stellar evolution. By studying their properties, such as their temperatures, masses, and compositions, astronomers can piece together the life cycles of stars and gain insights into the history of our galaxy. Moreover, white dwarfs are involved in some of the most energetic events in the universe. In binary systems, where a white dwarf orbits a companion star, it can accrete material from its partner. This accretion can lead to thermonuclear explosions on the surface of the white dwarf, known as novae, which can briefly outshine entire galaxies. So, while they may be the cooling embers of stellar evolution, white dwarfs are far from dull. They are fascinating objects in their own right, offering valuable insights into stellar life cycles, the nature of matter, and the grand cosmic dance of birth, life, and death among the stars. Thank you for joining us on this cosmic adventure. The universe is full of wonders, and these strange stars are just a glimpse into the mysteries that await us. From the pulsating beacons of pulsars to the mind-bending density of neutron stars, we've explored the extremes of physics and witnessed the awe-inspiring power of the cosmos. But this is just the beginning. As we continue to explore, to push the boundaries of our knowledge and technology, who knows what other strange and wonderful objects we will find lurking in the cosmic shadows? The universe is full of surprises, and it's this sense of endless discovery that makes astronomy such a captivating field. So keep looking up, keep questioning, keep exploring, and never lose your sense of wonder. The universe is vast and full of secrets, and it's up to us to unravel them, one cosmic discovery at a time. Until next time, keep exploring the cosmos.